Inequality algebra satisfies many of the same rules as normal algebra. For example, if we had to solve the inequality x subtract 2 is greater than 3, then it would be a perfectly valid operation to add a constant to both sides. If we add 2 to both sides, we can conclude that x is greater than 5. Similarly, if we began with something like x plus 1 is less than 7, it would also be a perfectly valid operation to subtract a number from both sides. So if we subtract 1 from both sides, we can conclude that x is less than 6. If we had 1/2 of x is greater than or equal to 2, it's a perfectly valid operation to multiply both sides of this inequality by 2 so that we can conclude that x is greater than or equal to 4. If we had 3x is greater than 12, it would be perfectly valid to divide both sides by 3 to conclude that x was greater than 4. So are there any differences at all between inequality algebra and regular algebra? Well, suppose we started with this situation. Suppose we had to solve negative x is greater than 2. Could we just do this by multiplying both sides by negative 1? That would give us that x is greater than negative 2. Now, can we do that? Well, let's have a look at this in a slightly different way. If we started off with negative x is greater than 2, as we did, and if we follow the rules we've already established, let's add an x to both sides. Negative x plus x would give us 0. 2 plus x would give us 2 plus x. Now let's subtract a 2 from both sides. 0 subtract 2 would be negative 2. 2 plus x subtract 2 would just be x. And let's rewrite that in a slightly different way. Negative 2 is greater than x is the same thing as saying that x is less than negative 2. Now let's compare that to our starting place, which was negative x is greater than 2. We could have gone straight from our starting place to our conclusion by multiplying by negative 1, but if we do that, we also have to reverse the direction of the inequality. So an important rule of inequality algebra is that when multiplying or dividing an inequality by a negative number, the direction of the inequality is reversed. Let's look at some inequality examples. Find the set of values for x such that 2x subtract 4 is less than x plus 6. If we start with 2x subtract 4 is less than x plus 6, we can subtract an x from both sides. That will give us x subtract 4 is less than 6. We can add 4 to both sides. That will give us x is less than 10, and there is our answer. And we are going to introduce another way to express answers to questions like this, and that is using what is called set notation. When we use set notation, we express all the values we're interested in between two curly braces. And the set notation consists of two parts. Firstly, we say we are interested in values of x, and then we have a colon, following which we give restrictions on the values of x. In this case, our restrictions are that the value of x must be less than 10. Occasionally, there is some extra detail given in the first part. We might want to make it very clear that x is a real number under the condition that x is less than 10. This first part is not seen too often, but you should be aware of its use. Find the set of values for x such that 5 subtract 3x is less than or equal to -4. So starting with 5, subtract 3x, it's less than or equal to -4. We can add 3x to both sides, giving us 5 is less than or equal to 3x subtract 4. We can add 4 to both sides, giving us that 9 is less than or equal to 3x. And then we can divide by 3. Because 3 is a positive number, we don't have to reverse the direction of the inequality. We have that x is greater than or equal to 3. In set notation, we would write values of x such that 3 is less than or equal to x. Here is an example where there is a little more to do. Find the set of values for x such that 2 lots of x plus 7 is greater than 6 subtract 3 lots of x subtract 1. So we're starting with 2 lots of x plus 7, that is greater than 6 subtract 3 lots of x subtract 1. Let's try expanding all the brackets. We'll have 2x plus 14 is greater than 6 subtract 3x plus 3. In other words, 2x plus 14 is greater than 9 subtract 3x. Now why don't we add the 3x to both sides? That will give us 5x's here. Why don't we subtract 14? That will give us -5, and therefore our conclusion, dividing by 5, is that x is greater than -1. In set notation, we could say that we have values of x for which x is greater than -1. In this example, we have two inequalities. We are asked to find the set of values of x such that 2x subtract 4 is less than x plus 6, and 5 subtract 3x is less than or equal to 4. What we have is simultaneous inequalities. Now you may have noticed that we've done both of these two examples individually already. We solved 2x subtract 4 is less than x plus 6. That was our first example, and our conclusion there was that x was less than 10. We also solved 5 subtract 3x is less than or equal to -4. Our conclusion there was that 3 was less than or equal to x. We need to find the set of values of x where both of these things are true, because we are asked an AND question. One way of visualizing this is to use a number line. Our first inequality was true for all values of x less than 10. We can visualize that in this way. The line that we have drawn underneath our number line represents all the values of x in our solution set. The open circle underneath the 10 indicates that we are not including that value. Our second inequality had the solution values of x greater than or equal to 3. We can visualize that using the second line. The solid dot underneath the 3 indicates that we are including that value. In this question, we want all of the values which satisfy both of these inequalities. We can visualize that by looking at this red line, which is where the previous two lines overlap, where they are both true at the same time. So this diagram helps us to see that the values we want are all values greater than or equal to 3 and less than, but not including, 10. So our solution to the question is that we want values of x greater than or equal to 3 and also less than 10. In set notation, we could write values of x such that 3 is less than or equal to x is less than 10, but there is also an alternative. The first inequality in set notation had solutions values of x such that x was less than 10. The second inequality in set notation had solutions values of x such that 3 was less than or equal to x. If we want to say all the values in this set and all the values in this set, then we use this notation. Looks a little bit like a lowercase n. In fact, n is quite a nice way to remember it since this is an and. But this symbol means the things which are in this set and which are also in this set. Here is a similar example. Find the set of values for x such that 5x subtract 15 is less than 6 subtract 2x, and 2x is less than or equal to 7x plus 10. We haven't done these two things previously, so we're going to have to solve them both on their own. So if we have 5x subtract 15 is less than 6 subtract 2x, let's start off by adding 2x to both sides. And now let's add 15 to both sides. And finally divide through by 7. We have a solution to the first inequality, or in set notation we could write that as values of x such that x is less than 3. For the second inequality, 2x is less than or equal to 7x plus 10. We could begin by subtracting 7x from both sides, and then we could divide through by negative 5 to give us a single x on this side and a negative 2 on this side. But we must remember, if we're dividing by a negative number, we must reverse the direction of the inequality. So we have x is greater than or equal to negative 2, or in set notation, values of x such that x is greater than or equal to negative 2. Again, we can visualize the solutions on a number line. Our first inequality had the solution x is less than 3, so we have a line indicating all values less than 3 and not including the 3, which is why we have the open circle there. The second inequality had solutions x is greater than or equal to negative 2, so we can visualize that by a line which starts at negative 2 and has all values greater than that, and the negative 2 is included as signified by the closed circle. The values for x where both of those inequalities are satisfied is the region where those two lines overlap. Everything from negative 2 inclusive up to positive 3 not inclusive. So our final answer in this case is every value from negative 2 inclusive up to 3 not inclusive, or in set notation we could either give that answer as values of x between negative 2 and 3, or we could write this in the same way we did previously. We could say it's the values of x which are less than 3 and the values of x which are greater than or equal to negative 2. It would not matter which way round these two set brackets are. The important thing is we want the things that appear in both of them. A similar example, but with a subtle difference. We have two inequalities, but we are asked for the values of x such that one or the other inequality is satisfied. Possibly both, but we are not demanding that they are both satisfied. Let's solve them both separately. So the first one is 3 lots of x subtract 1 is less than 2 lots of x subtract 2. Expanding all the brackets there, we have that 3x subtract 3 is less than 2x subtract 4. If we now subtract 2x from both sides, the 3x subtract 2x will become a single x. If we add the 3 to both sides as well, we'll have that x is less than negative 1. Or in set notation, we want values of x such that x is less than negative 1. The other inequality, 5x subtract 1 is greater than 6 subtract 3 subtract 4x. We'll have to be a little careful with our expansion here. The left-hand side is already fine, but if we expand this, we'll have 6 subtract 3 plus 4x. In other words, we will have 5x subtract 1 is greater than 3 plus 4x. Now if we subtract 4x from both sides and add 1 to both sides, we'll have that x is greater than 4, or in set notation, values of x such that x is greater than 4. On a number line, we can represent the solutions to the first inequality, x is less than -1, by a line representing every value from -1 downwards, not including -1. The second inequality had solution x is greater than 4, so we can represent that by the line including every value from 4 upwards, not including the 4. If we are interested in solutions to one inequality or the other inequality, then we would have to consider all of these possible solutions. In other words, our final solution are values of x which are less than -1 or greater than 4. We could either write this by saying that x is less than -1 or x is greater than 4, or in set notation we could say that we have values of x which are less than -1, values of x which are greater than 4, and the symbol for values in here or values in here is this symbol. It's the same as the previous one but upside down. It's a little bit like a large capital letter U. Notice that if this question had been an AND question instead of an OR question, then in this case there would be no solutions. We can see that because the two solution sets to the individual inequalities have no values in common.